So to continue, there is one thing about the BCCFT that we need to discuss, and that's the following. Well, okay. You remember we had the operator product expansion C of Z1, B of Z2 went like 1 by Z12 plus and B of Z1, C of Z2. Right? Now, okay, the term that appears in the zero part of this operator product expansion is plus normal ordered C of Z1, B of Z2. And then to get all the other terms in the operator product expansion, we could just Taylor expand the Z1 around Z2, as usual. Okay. Now, now suppose we take Z1 to Z2. There's the singular term, and there is the term that is the first non-singular term. That's just C of Z2, B of Z2. Okay? That quantity, C of Z2, B of Z2, C of Z, B of Z, we're going to give a name. We're going to call it the ghost current. The ghost current. Okay? Now let's look at the operator product expansion of this ghost current with C and B. Okay. So J of Z, C of 0 clearly goes like C of 0, well, C of Z by Z plus non-singular, because the BC part contracts to give you 1 by Z, and then everything else is non-singular, so this we can replace by 0. So C of 0 by Z. And similarly, we have J of Z, B of 0 goes like minus B of 0 by Z plus da, 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 da. We get minus B of 0 because you have to take the C through the B, that's a minus sign, then contract, and then you get the B of 0. Okay? So if we take this, the charge corresponding to the ghost current, okay, and we ask what is the commutator of that charge with C, with the operator C. That's, you know, this minus this, so it's right, it's this, so we'll get 1, right, we'll get back C. So so the ghost charge, let's call it QG, is integral JZ dZ. Okay, so this is a charge. Whose current is entirely analytic. JZ bar is 0. JZ is JZ. So this is the ghost charge, maybe with 1 by 2 pi, 1 by 2 pi I, whatever our usual convention for the charge, maybe 1 by 2 pi I. Yeah, 1 by 2 pi I, and then we will get that the commutator of QG with C of x is equal to C of x, C of z. Whereas the commutator of QG with B of z is equal to minus B of z. Okay? So this the C operator carries ghost charge 1, and the B operator carries ghost charge minus 1. Okay? So what is this ghost charge? This is a conserved current for a symmetry. What is the symmetry? Well, we're just phasing C by 1 and B by minus 1. Right? It's the symmetry of the operation where C goes to C times e to the power I alpha, B goes to B times e to the power minus I alpha. And in the action of our theory, okay, every time there was a B, it multiplied a C. So that's clearly a symmetry. Is this clear? Just rotational symmetry. Okay, so you've got a you've got, you're counting the number of C's minus the number of B's. That object is generated by this current called the ghost charge. Okay. So now there are various things we want to do with this ghost charge. Okay. The first of these is to look at the operator product expansion. The operator product expansion between the stress tensor and J ghost of 0. J is conserved because it's analytic. It's a product of two analytic fields. Therefore, it's analytic. So del z bar of Jz is 0. So that's conserved. But of course, it had to be conserved from the Noether prescription anyway. This is global. Well, you can make it local to the following extent. This J is analytic. So any moment of it is also a conserved current. Okay. So to that extent, you get something like a current algebra associated with this J. No, there's no gauge field. Just yeah, so that's not what it's in the same way as local as like the Virasoro algebra came about from translations. It's not local in the sense that you can't put an arbitrary function on it. Right. So it's only these analytic functions. I mean, there's no gauge field.
So one can't even gauge it.
You can gauge it if you want to. That will introduce a gauge field. Why should we? It's a global symmetry. No. This is just a global symmetry. Okay? It's just a general fact in conformal field theories that global symmetries often, go ahead of themselves, generate infinite global symmetries, because global symmetries are often generated by a current which is holomorphic. And once you've got holomorphy, you've got all the moments of that. Just that. Nothing. There's no. We're not modding out the theory by these rotations. That's another way of saying it.
Oh, it's a real symmetry.
It's a real symmetry. Exactly. Exactly. We're not going to say that. We're not going to declare that only zero charge under this is physical. Okay. It's just there. Okay. Now, so for this we need the formula for the stress tensor. Can somebody help me? Somebody with their notes? Well, this was equal to what is it? Del BC minus lambda del of BC. Okay, excellent. So this, we want the OP of this with, I've written it as CB. Now maybe I should check whether Polchinski defines it as BC. It's a question of whether C has charge 1 or B has charge 1. I can't even find it. We'll define it this way and then we'll switch signs if it's necessary. Okay. So let's move. So let's compute this OP. Okay. Here. So let's see what is the most singular term in the OP. The most singular term is when the B contracts with the C and the C contracts with the B. Okay? So let's do that contraction. So we get the C contracting with the B. So from this term we pick up a minus sign because we have to take it through. We get a 1 over Z. So let's say that this is at 0. Okay? So we get 1 over Z. And here we get a 1 over, so we get a minus sign, 1 over Z. And then a del Z of 1 over Z. So the first term is this. And the second term is minus lambda del Z, and here we get a minus sign and a minus 1 by Z square. Do you agree? Okay, excellent. So this is 1 by z, 1 by z cube with a plus sign. And this is with a minus sign. It's minus, minus, and then the derivative gives us another minus, minus 2 lambda times identity. Okay, good. Now, now let's go ahead and compute the rest of it. Okay, computing the rest of it is what? In order to compute the rest of it, we want to compute the terms with one contraction. Okay, so let's look firstly at C contracting with B. So that's minus 1 by z times del B. This is at z, but since only 1 by z, that's same as 0. Del B times C. D is evaluated at 0, effectively, for the singular part. Okay, that's the C contracting with B. C contracting with B, I get a minus and 1 by z. That looks good. Then what about the B contracting with C? So once again we have a minus. Now we've got a del z of C of z by z times B of 0. Is this okay? Please check my minus signs carefully. Okay, so this will give us, okay, we'll evaluate it later. And then there is a minus lambda, and once again we could have both possibilities. So del z, and we'll list the two possibilities. The first one is when C contracts with B. So both of them will require us to go through with so the minus will become plus. C contracts with a B will give a 1 by z. So that's B of z, C of 0, plus, and the other one is C of z, B of 0, the whole by z. Is this okay? Okay. So now let us proceed. Let's first collect the terms that are 1 by z square. So the 1 by z square terms come when both these guys hit the z. So we will get CB, the first one gives CB by z square. So 1 by z square times CB, and the second guy gives the second guy gives
but this is identical to 0.
That's right.
Yeah. Yeah, because we have to evaluate it at 0.
Exactly. Evaluating at 0, this is just 0. Exactly. BC plus CB, basically. So just CB by z square. But CB was just JB. JG. So that's J host at 0 by z square. Okay. What remains is now the 1 by z terms. So let's keep it all. There was 1 minus 2 lambda by z cube plus this object plus the 1 by z terms. So the 1 by z terms, so let's see. So okay, it's a bit of a pain, but let's get it. Now look. Do you see so let's try to take a few shortcuts. It's the derivatives on anything that contains a z. See, where did the derivative come from? It came from this derivative. I'm sorry, did I mess it up?
Is the del BC contracting with the CB and the second contraction?
The del B, but he is asking correctly why the derivative. So this was del B, we got this from del B contracting with C, right? So you're right, this should be only on 1 by Z. Thank you. Right, because it was just this. So just on the contraction. Thank you very much. Del B, and that didn't change our yeah, okay, thank you. So this, okay, good. So this term is 1 by Z square times C of Z times B of Z. Setting C to 0, we've got CB, but the next term will be
yes. There's a term over there. The first term is also 1 over Z.
Is also 1 over Z. Yes, we've got many terms. So one of the terms, the one from here gives us del CB by Z. Okay, that's this Taylor expansion. Then there is minus del BC by Z. And then there is this term here. Now let us look at this term. This term actually we can just write as follows. This term by itself is analytic. Do you see? Because this thing is, because B of 0, C of C 0 and C of 0, B of 0 cancel each other. So all that's left behind here is the order Z term. Z and Z cancel. So it's not going to produce any non-analytic. Okay, so this term you can forget about. So this term is simply del of CB by Z. So plus del JG by Z. Okay, so we what? L1 does not annihilate JZ, exactly. So this is not a primary operator. L1 does not annihilate JZ, correct. Okay, so we've got the OP of the stress tensor of the coast current. It's got the terms that you would expect had this J been a primary of weight 1. Okay, but it's also got this additional piece, this additional singularity. No, quasi-primary just means that these parts are what you expect them to be. Okay? Can have anything here. So quasi-primary is fine.
Quasi-primary can have the Q.
What?
I thought the quasi-primary can have 1 over Z.
Can't have 1 over Z cubed. No, I think quasi-primary just this stuff is, yeah. This part is just okay. I can't remember how we define quasi-primary, but just under SL2R, right? Under SL2R, I think this is just fine. I can't remember exactly, but I think it's just this part. Yeah, because all we use is, I would have to go back and check, but I think it's just okay. Okay, but anyway, this is what it is. It's the thing that has this piece. Okay, now what we want to do is to figure out what it means that this thing has this piece. Okay, so we're going to undertake an exercise sort of similar. We're going to undertake an exercise sort of similar to what we did with the stress tensor. The stress tensor under the OP of the stress tensor with itself had this 1 by Z to the 4 piece. That told us that it did not transform just under diffeomorphism. It also transformed under Weyl transformations. Okay? So in a very similar way, this term here will transform not just under diffeomorphisms, but also under Weyl transformations. Okay. So how's that going to go? Well, let's see. under the object epsilon of z, t of z, under the current generated by epsilon of z times t of z. Okay? These paths give you the transformation due to diffeomorphisms. So we want to see what the additional transformation of J is under this current. Okay? So we want to look at the pole of epsilon of z, t of z, with Jg at 0. Okay? So that is 1 minus 2 lambda. And now, so that was what we got from here. And now what we're supposed to do is to take the pole. This was a z cube. Okay? So we get epsilon double prime of z, epsilon double prime of at 0, divided by that's it. Or more, suppose we wanted to do the thing at a w by 2. So this will be epsilon w double prime at w. You know, the transformation and the Weyl transformations at that point. Okay? So this is how this object here changes. Okay? This is how this object here changes under a conformal transformation, which is epsilon of w. Now we want to figure out how J changes. We want to figure out how J changes under an arbitrary Weyl transformation. Okay? So we'll use the same trick as before. The trick was that the Weyl transformation, this epsilon thing, induced a Weyl transformation. The Weyl transformation was epsilon prime. You remember? Because dz, the change in the Weyl factor, the small change in the Weyl factor is epsilon prime. So this delta phi, this delta, so delta phi, the Weyl factor, is epsilon prime. So this is 1 minus 2 lambda by 2 times delta phi, del of delta phi. Under an infinitesimal Weyl transformation, this is how J changes. Okay? And therefore we conclude, okay? Therefore we conclude that the change of J under an arbitrary, infinitesimal Weyl transformation is simply 1 minus 2 lambda by 2 of, this is J mu, del mu of delta phi. Because this was the analytic part. You may just make it a covariant equation. Okay. Now, let me try to write this as a formula for the change of del dot J. Okay, this is equal to 1 minus 2 lambda by 2 times del squared delta phi. What? Exactly. So now, you see, we want to figure out what this del dot J can be. Okay, so del dot J is some scalar quantity, okay, that transforms under Weyl transformations with a del squared phi. Okay, but we know that R transforms under Weyl transformations with the del square phi. Okay, R is the only reasonable thing it could be, because del dot j is a dimension 2 object, it's a scalar. R is a dimension 2 object, it's a scalar. Okay, so basically this quantity here allows us, when we compare the transformation coefficients of R, this quantity allows us here to pull out. So basically what we're concluding here is that del dot j is equal to some number times R. Okay, and when we can pull out the number from this comparison. Okay, I'm not going to go through the algebra to pull out that number, but Polchinski quotes it, I believe, in a problem. Okay, so guys who are doing problems, do problem number 3.6 in Polchinski. Okay, that tells you that if the coefficient of ZQ, okay, Polchinski tells us that this number is minus 1/4 the coefficient here. So it's minus 1/4 times 1 minus 2 lambda, 1 minus 2 lambda.
This was sort of the general statement about anything equal to with a test tensor has a 1 over z cubed.
Exactly.
Or we're saying that the only thing that can have this kind of 1 over z cubed would have to be r up to some kind.
Exactly.
Would have its derivative.
Exactly. We know that in flat space the current is divergence free, holomorphic. Okay? Now we do a Weyl transformation. The fact that it's not changing under Weyl transformations like a primary would allows for the possibility that del dot j will no longer be 0. And in fact we can calculate what it is. Okay? And we calculated it. So this object here, while a conserved current in flat space, is not conserved in an arbitrary manifold.
Usually, for conserved current, they are also null, but then the del dot j becomes a null primary.
Del dot j becomes a null primary. Yes, yes. So just in flat space here.
The fact that it's
No.
not a primary is related to that it's not conserved. I'm just trying to.
No, you know, the conservation in flat space is simply the fact that it's analytical. Okay? And that conservation tells you that h is equal to 1. Okay? So that the equation that you were talking about would be the equation del bar of jz is equal to 0. And that in flat space continues to be true. So you're doing just representation theory in flat space. You don't see this issue at all. Okay? However, yeah, it's not primary, it's true. It's true. It's true. It's true. Yeah, it's true. It's true. It's true that it's not primary. So it's just not the head of a representation. So, right, you're right. Basically, it's a conserved descendant. Okay, what we could do is to try to figure out what it is a descendant of. Okay, and then work out the representation theory of that object. I mean, that's how representation theory would go. Okay, now actually I should be able to answer that question. What is this a descendant of? It's, however, you can have null states even in non-unitary theories.
That I can certainly have, but then this proof that whenever you have a null state,
Yeah.
that this primal, that it is a primary, this kind of things you prove by taking norms. That this is also a descent, it's a primary and a descendant, therefore it is null. This kind of statements when you try to prove.
Yeah, but I'm. Oh, you mean for del dot j, for the quantity del dot j. Yeah. But as you say, j itself was not a primary. So there are many things about this we would have to think through in different language. Yeah.
For lambda equal to half, this j will be a conserved current.
J is a conserved current.
And there will be no anomaly. So this is an anomaly-free theory.
Exactly.
So what
Exactly.
special theory does it correspond?
It corresponds to free fermions. Let's since you asked this question, I should have said this yesterday. So let's go back to our formula for the central charge. Yesterday, we had the central charge was, please help me somebody, -2 plus 12 lambda minus 12 lambda square. Now, let us set lambda equals half. So we get -2 plus 6 minus 3, which is equal to 1. Okay, this is exactly the central charge of 2 free fermions, or 1 complex free fermion. Okay,
Or a boson, I mean, just from the central charge or a boson.
or a boson, but here we're looking at an anti-commuting, a theory of an
Okay,
anti-commuting field. So if you take a Dirac, a complex Dirac particle,
Yeah.
okay, actually, can you see? Do you see
If I don't look at dimensions,
dimension? That's even here. So.
will be dimension
So lambda was equal to, yeah, so C, dimension of C, dimension of C was 1 minus lambda, so that's equal to half. And dimension of B was equal to lambda, which was also equal to half. Agree, exactly what you expect from a free fermion. Psi and psi by each dimension half B.
lambda equal to, yeah, now everything is
Everything matches, right? It's central charge 1, it's got, the dimension is half and half. Okay, so this is a particular theory because it's got, it's like a Dirac field, it's completely the chiral part, anti-chiral part being treated the same. This is a particularly nice theory. In that theory, psi bar psi is actually a primary operator. That is your observation. This vanishes. So it's a particularly nice theory. In fact, that is a unitary theory. Okay. This is a theory we will encounter and study in great detail because it will occur in the world volume of the superstring.
But still the chiral current will not be conserved even in 2 dimensions. This is just the usual number current.
The chiral current will not be conserved if you turn on a gauge field coupling to that current.
Right.
This is a separate question. We are asking, is there a non-conservation that's not proportional to the field strength of the gauge field you turn on coupling to the current? Is there a non-conservation proportional to curvature? These are 2 separate questions.
Yeah. Just the manifold.
Yes. Okay? And in that case, even this chiral current is conserved. I mean, there's no curvature coupling issue. I mean, conserved, it's, even on our arbitrary manifold. Yes, exactly. Yes. And that will be there. That, in fact, is the fact that the current algebra has a central term. We could work that out if you wanted. It's in the JJOP, there is a 1 by z square. That is associated with the fact that there is this F term. Okay, because anyway, we'll come to that when we use it. Okay, because that is the thing that tells you how J transforms under its own, under symmetry transformations. Okay, we'll return to that when we're interested in current algebra in this question. Okay, so these are separate non-conservations. Okay, and the fermion there is perfectly conserved, just an arbitrary background. Okay, excellent. So, but this is something to note and that we will use later, that this BCCFT, though we get it at this value lambda equals 2 for the host sector of the bosonic string, there is another very special value, namely lambda equals half, in which it's a much more familiar thing. Actually, let me take 2 minutes because this may not be totally clear to everyone, and will help you build your intuition. What at all the BC action has to do with the fermionic action? Let me explain that. So this is an aside. We're coming back to what we were discussing.
Is the fact that these 2 interesting values of lambda, sort of lambda is 1 over lambda, is that? Like
2.5.
or is this
I don't know of any of significance of that. We will encounter other values of lambda also that are significant. Okay. Yeah, this is this thinning model, right?
Yeah, then you go to this boson.
Exactly. So this is the thing that this is the thing that is dual to like a sine Gordon. It becomes a massive theory. It goes to the sine Gordon model. Okay. Right. Okay. So and actually one easy way of understanding that is boson. Oh, but I haven't told you about bosonization. Maybe I'll quickly tell you. But anyway, first let's one at a time. Okay. Let us first just very briefly, since this fermion field has come up, let us very briefly see why the action we wrote down, if I just replace B with psi and C with psi bar or vice versa, is the usual Dirac action.
Yeah.
Let's look at that. Okay, so the usual Dirac action is what? It's psi bar del slash psi. Okay, we're in Euclidean space. Okay, so our del slash is made up of d dot gamma, where the two gammas are both Pauli matrices. Now you have a choice for what to choose for your Pauli matrices, and let us choose the following. Let us choose, or maybe what we should do is work in Minkowski space and, okay, let's, Minkowski space. Let me just work in Euclidean space. It'll be a bit easier. Okay, so we get psi bar, or should I? Okay, I'll work in Minkowski. Let me work in Minkowski. So then this is psi dagger gamma 0 times del slash psi. Now what should I choose? I think I should choose gamma 0. Gamma 0 should be chosen to be I sigma 2.
Yeah.
Because gamma 0 should be non-Hermitian. Suppose I want to keep everything real. I want to keep all my matrices real. Then I'm basically forced to choose gamma 0 to be I sigma 2. Okay? And then I will choose gamma 1. If I want to keep my matrices real, sigma 2 is the only imaginary Pauli matrix.
So you want everything real.
Suppose I want to keep everything real. I'm not sure. Maybe I should. There are many choices, but I want to get the one that will be most nice. Let me try this. Let me fool around for 2 minutes. I think I'll get it. Okay. So sigma 1 is equal to sigma 1. Let me try this. Okay. So then this will be psi star of I sigma 2 times del 0 I sigma 2 plus del 1 of sigma 1. Del 1 sigma 1. Okay. Now,
Sigma to sigma 1 will yield some sigma 3.
and this, everything will give sigma 3s, right?
Yes. No. Yeah.
Sigma 3 is an identity.
Sigma 3 and identity.
And identity. So that's good.
Yes.
Everything will be diagonal, which is what I wanted, right? So psi. So now let's do this. Sigma 2 times sigma 2 is identity.
Yes. And minus 1.
And minus I times I is minus. So we get psi star.
Minus del 0.
Psi star of minus del 0 minus del 0. And here I get sigma 2 times sigma 1 is minus I sigma 3.
Yes.
And then I have the I, so that makes it
Plus sigma 3.
plus sigma 3. So I get plus del 1 minus del 1 psi. Okay? So suppose we wrote psi is equal to psi plus psi minus. Okay, and psi star, psi complex conjugate is psi plus star psi star. Then this object is psi plus del minus psi plus with a minus maybe, psi plus star del minus psi plus psi, overall minus plus psi minus star del plus psi minus. Okay? Now when we analytically continue, plus and minus go to z and z bar as usual. So if the psi plus is what we'll call psi plus, we'll replace by okay, let me, so as not to clutter notation, just forget about this part. These two are decoupled.
Yes.
Let me look just at this part. This is the holomorphic part. This is like, this will be like the B bar C bar, which we don't even write down. So this is the BC. Okay, this will go to psi, and psi star I'll replace by psi bar.
Yeah.
So psi bar del z bar psi. Okay, now instead of psi bar if we wrote B, and instead of psi we wrote C, it's the same action we had before. Okay, so what's the lesson? The lesson is that Dirac particles in 2 dimensions, firstly, you take the Dirac equation in 2 dimensions, you can make it real. Right? You can choose your sigma matrices so that sigmas are real. Okay? So we work in that basis. Then it's consistent. Okay, anyway, so we work in that basis, and then with an appropriate choice of sigmas, we can, well, always the action breaks up into action for 2 decoupled fields. But with an appropriate choice of sigmas, these 2 decoupled fields are just the top and the bottom components of your spinner. A psi plus and a psi minus. Okay? And the psi plus and its complex conjugate form a holomorphic field. And the psi minus and its complex conjugate form anti-holomorphic fields. Now there are 2 of these. There's the field and its complex conjugate. And that has exactly the same action as C and B and C bar and B bar. Okay? So, so the BC system, one simple example of the BC system is just free fermions in 2 dimensions.
That was totally Weyl BC system.
Classically, it was totally Weyl. Yes.
It is only quantum effect that made this
Absolutely. Absolutely. Absolutely.
So if you try to calculate determinant of this quantum PRST, determinant of this is going on the sphere,
Yes.
then you will see this kind of problem.
Yeah, in particular, this is telling us about the 0 modes. Okay, let me explain that immediately. Okay, so sorry. So this was just a divergent to tell you about the size. You understand it now. We've forgotten about it. We'll come back. Okay. So now we've got this beautiful formula, and I want to explore its consequences. Okay. Now what does this mean? This thing tells you. Okay. This thing tells you that if you are on a certain manifold where R is not 0, locally the current is not conserved. But more seriously, even the global charge need not be conserved. Okay? In order to see that, let us remember that if we integrate del dot J, what that gives us is the difference between charge initially and charge finally. Okay? So, this is telling us that if the integral of R is non-zero on a certain manifold, ghost number is not conserved.
The ghost number is proportional to the Euler characteristics of the
Exactly. Now let us try to make this a quantitative statement along the lines Upmanyu is requesting. Can any one of you remember what integral r, I need the factor, to get the genus? Give me a minute. Does anyone remember it? The integral of r is related to the genus with what factor?
Root gr for sphere is 2.
Root gr and no half root gr, right?
Yeah.
Just Euler. Just a minute. Just a minute. I'll pull it out. Sure, it doesn't have a boundary. Just a minute. Chi is equal to 2 minus 2g, but what is chi? So, okay, let's first write down the first formula. Chi is equal to 2 minus 2g, and that's nice. And now we want a formula for chi. Just a minute. I'm really sorry, just give me 1 second. 1 over 4 pi root g r? Yeah, where are my 4 pi's going to come from? Just yeah, no, for what I want. Oh. Maybe because my charge had a 1 over 2, yeah, that's the 2 pi is the charge. Yeah, okay, good. So chi is equal to 1 over 4 pi square root gr. Okay? And, okay. Now, what I'm going to do is to try to understand what this means for ghost number conservation. So, Indrail tells me you shouldn't think in terms of charge conservation because there's no future and no past on a sphere or a torus. Let's do it in a way that will satisfy. Okay. So, what I want to do is to look at a path integral. Okay. So, what I want to do, let us remember what the definition of the current was. Okay? If I make a transformation, yes. 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 No, it's, I mean, totally different. You could have had a theory with a Weyl anomaly, like the theory of a fermion. Has a Weyl anomaly,
but does not have this problem.
But does not have this issue. These are totally different. This is a statement about the symmetry in question. Okay, so let's see. So we have integral, what have we concluded? That integral del dot j is equal to 1 over 4 pi times 2 minus 2g, because chi is 2 minus 2g, times whatever this was, minus 1 by 4 into 1 minus 2 lambda. Okay? Now, how am I going to relate this to anything? Okay, what I want to do is the following. Suppose I've got my, my theory. So my theory is integral dB dc exponential of minus s ghost. Okay, SG. And suppose I put some number of insertions into this. Okay, so I put ACs. So C at sigma 1, C of at sigma m, let's say. So MCs. And I put NBs. B of sigma 1 prime, B of sigma n prime. N of them. Okay. Now what I want to do, is the change of variables. I want to make the infinitesimal transformation. C goes to e to C times 1 plus I alpha, infinitesimal rotation, and B goes to B into 1 minus I alpha. Okay. Now, it was precisely this manipulation. If this had been an invariance of the action, okay, that allowed us to conclude that we had conservation of current. Okay, let us review that derivation for 1 minute. What we did was we made alpha a function of position. It's small, we made it a function of position, and we said we had this integral. We said we made a change of variables. Okay, we made a change of variables when we did that. Okay, and we concluded that we assumed that the change in the action under this process, change in the action and measure, was 0.
Is the same Fujikawa argument for anomaly?
But I'm just going back to what we talked about when we derived Noether's current. Just reminding you of that.
Yeah.
Okay? Yeah, but it's related to that. Yeah. So what we did was we made this change of variables. We assumed that the change of the action was 0. Okay? And so then we did the following. We said that then the only change could be because alpha was a function of position. Okay? So we said under this change of variables, we said Sg goes to Sg in terms of the new variables, plus integral j del mu epsilon j mu. Okay?
Alpha G in this case.
Del mu alpha j mu. Absolutely. Okay? And then and then these C's and B's also changed, and we derived from that this word identity. Right? The word identity, which was insertions of J's with the old C's and B's plus modified C's and B's is equal to 0. Now what we find, okay, and that told us that del dot J was equal to 0 unless it hits some other point. Okay? Now what we know is that del dot J is not equal to 0. Yes. So it's basically telling you, by integrating this equation, that even when alpha is constant, we get a change in the action. You see, because this was the definition. This is how S transformed under one of these alphas. And since del dot J was equals 0, is basically the statement that when alpha was constant, the measure times action did not change. Okay, so del dot J not being equal to 0 tells us that we have a change even when we have an alpha, constant alpha prime. Okay, so now let's do this change with a constant alpha, accounting for the fact that the action is not invariant but picks up this additional factor. Measure times action is not invariant, but picks up this additional factor. Okay?
If I look at the action, it looks like it is invariant under changes in phi. So
It's a cutoff thing. It's the measure really. It's the usual thing with anomalies.
No.
Okay? So because it's not invariant, okay, because this thing is not invariant, what we're going to get is a term here just from the action. Now we do it for this global transformation. We also get a term for each insertion. So each of these C's picks up an e to the power I alpha. Each of these B's picks up an e to the power minus I alpha. Okay? And the whole measure, the whole action, picks up the integral of del dot j. Okay? So now the only question left is Sg goes to Sg plus del dot j with what factor here? I believe it was 1 by 2 pi I. Just give me 1 minute. Yeah. In order to get, you know, the thing to be consistent with the current, I by 2 pi integral j del dot rho. So with this, there's an I by 2 pi. Okay, this corresponds to the fact that when we wanted to build charges out of currents, how do we know this? This corresponds to the fact that when we built charges out of currents, the charges were always 1 by 2 pi I times integral currents, so that the transformations are just given by poles in the OP. This is that same 2 pi I. Okay, so this is that normalization that we want to keep track of. Okay, so now we're all set, and now we'll see if we can get it right. Okay, so let's see. So I have, and just, was it e to the power? E to the power, s changes with the e to the power minus s goes to e to the power minus s plus I by 2 pi integral del mu alpha j. This is the claim. Okay. So I'm sorry for all the mess, and I hope we get it right at the end of all this. So now let's do this, integrate this by parts. So this becomes a minus, and integral del dot j. We've kept alpha to be constant, so we can pull it out. Then we do integral del dot j. Now integral del dot j is second line, yes.
Should that be multiplied by 4 pi, not divided?
This should be.
So delta j in particular would be on both sides and then integrated. So it will be pi to 4 pi.
You're right. Thank you. That will be needed. So S, okay. So plus I alpha. Now the 4 pi and 2 pi cancel, so that's 2. No, 2 in numerator. 2 times 2 minus 2g. Now which factors have I taken down? Which minus have I taken? And that cancels this minus. Right? So by 4 times 1 minus 2 lambda. What is the chance this is going to work out?
So this 1 minus 2 times.
Okay, so we're going to calculate the phase. So phase, the change in phase. Okay, so the change in phase, delta phase, is equal to 2 minus 2g, so 1 minus g into 1 minus 2 lambda plus n, which was the number of c's, minus m. But you see, after we've done all these changes in phases and so on, we're left with the same integral. In terms of the new variables, we've got the same integral. Okay? So this change of phase, what we've concluded is that we've got an integral. We've got an integral which is equal to e to the power I times this phase times the same integral. So this integral is going to be 0 unless this phase is 0. Is this clear? Let me repeat the logic. The logic is we did a change of variables. The change of variables gave us action of the same form plus a known change. Okay? Each insertion picked up a phase. So after we account for all those phases, we've got back the same integral in different variables. So we've got an integral is equal to e to the power I times something times that integral.
You're going to get some theory between number of 0 nodes and BM.
Exactly. I just hope I get it right. Okay. So what we conclude now is that this path integral is 0 unless n minus m is equal to this quantity.
So it can also be g and m are all integers, but lambda can be anything. So this could also be some multiple of 2 pi.
What could be a multiple?
This whole thing, this delta phase, for the whole thing to remain invariant.
Yeah, but you know, we're going to do this for an arbitrary phase alpha.
Okay. Okay.
We've got an arbitrary alpha,
Okay. Okay.
so we can't.
Arbitrary alpha, right.
So it just has to be 0.
Right.
The coefficient of alpha just has to be 0. Okay? So what have we concluded from here? That's correct. So if you're going to get some well-defined, if you're going to get on a manifold of something well-defined, any of these things non-zero, lambda has to be something special. But for our case, it is something special. Right? Lambda is 2. So we have n minus m has to be equal to 2 lambda minus 1 into 1 minus g. Or let's write it as 2 lambda minus 1 into minus of this into g minus 1. N minus m. Have I got the minus signs wrong? I've switched two things. It's right. I took one sign because I took it to the other side. I've just done it so that, okay. And I'll write this as m minus n is equal to this.
Actually, C goes in e to power I.
Exactly.
That's why it is plus.
Oh, you wrote this. I'm sorry. You're right. You're right. You're right. You're right. N minus m is this. Okay. Let's be more specific. M was C's. So number of B's minus number of C's is equal to this. Okay. Now let us set lambda equals 2. So we get is equal to 3 into g minus 1. It's right. So quite amazing. With the help of, what was it, Wikipedia that told you the 1 by 4 pi? Okay. With the help of Wikipedia and even the signs of it. Okay. So what we conclude is that the number of B's minus number of C's has to be this. Now let us relate it to something we already know. Okay? We know that the number of B, you see, this we know on abstract grounds. This has to be 0 unless there is a certain difference between B insertions and C insertions. But we already know Exactly. We already know that we're going to get something non-zero, we're going to get something zero. That we're going to get something non-zero, the first time we get something non-zero is if we have as many B insertions as moduli and as many C insertions as conformal and killing vectors, unfixed diffeomorphisms that get met. Right? Okay? So that is going to give us something non-zero. So we conclude that number of moduli minus number of CKVs, people conformal killing vectors, has to be equal to 3 into G minus 1.
The derivation also directly tells that this quantity is related to the index. The quantity R.
Yes.
In more generally, whenever you have got zero,
Yes, yes,
zeros are
yes,
difference of
yes, yes, exactly, exactly. Exactly. So Indrani is pointing out that mathematicians like to define this. You know, when you've got an operator like this, the difference between the number of zeros of the operator and the number of zeros of its adjoint is called an index. And if you remember, the number of zeros of C was the number of zeros of this P operator. The number of zeros of B was the number of zeros of the adjoint. Mathematicians love this in these objects. You know, number of zeros of this minus something, and physicists love them for our own reasons, the reason being anomalies. And these are the same reasons. And what we've done here is use physics to write down a formula for the index of the operator P. That's basically what we've done. We did it through our own considerations, this ghost number, Weyl transformation, blah, blah, blah. Mathematicians will do it in their own way, but it's all the same thing. Okay? Fine. Now let's...
Does index theorem have any special name?
Oh, it probably does. I don't know. I don't know. I'm sure for the mathematicians it does. It's a very natural object. Yeah, but I don't know. Okay. Okay, now let's work this out case by case. First, let's take G is equal to 0. Okay, so now we get that the number of moduli minus the number of conformal killing vectors is minus 3. Now we know that the number of conformal killing vectors is 3. And I haven't proved it. Actually, we proved it. It's the number of zero modes of B is 0 on the sphere. How do we prove this? Let's quickly check that. Yeah, it's basically something with dimension 2. That's what's important. Okay, so see. What are we looking at? We are looking at the operator del z. First, let's check that the number of conformal killing vectors is 3. We've done it before in class, but we'll just do it again in slightly more modern language. Okay, so we want del z c. C is equal to 0. That gives us a 0 mode. So it's an analytic function of c. Okay, so anything that goes like z to the power m is equal to 0, 1, 2, blah blah blah. Okay. Now the danger is that it may not, this is all good everywhere except at the north pole, the point at infinity. We have to check whether it's regular at the point of it at infinity or not. Okay. So what we're supposed to do is to transform to the new coordinate. Now C transforms like dimension minus 1. Okay. Now let's see. Something that's del z is equal to something that's dimension 1 transforms out. It's always, to get the way right, it's always just work it out because the derivative transforms. So del z is del w by del z times del w. Okay? So C is equal to del w by del z CZ. CW. This is true for any conformal transformation. The conformal transformation that
Del Z over del W, right? CZ, because it's up.
del by del W. This is.
No. No, what I mean is in the C.
Uh-huh.
The C should transform.
You're right. Sorry. Because it's the opposite. Yes. Del Z by del. CW. Thank you. Okay. Now the W for us is 1 by Z. Okay. So let's work out del Z by del W. Z is 1 by W, so that's minus 1 by W squared. Okay. So minus 1 by W squared. So we get CZ is equal to minus 1 by W squared CW. Okay. So CW is equal to W squared CZ. Now CZ went like AN Z to the N. So it goes like AN by W to the power N. Sum over N. This has to not blow up at W equals 0. Okay, and that works if N is equal to 0, 1, 2. These are the three conformal killing vectors. We said this before, so I'm just saying. Now you see what has changed with B. Exactly, instead of 1 by W to the 2, we'll get W to the power 4. Okay, so this will become 1 by W to the power 4. Now which of these guys is well defined at W equals 0? None of them. So there are no 0 modes of B on the sphere. So there are no moduli for the sphere. Okay, so we've checked that this theorem that we derived abstractly in this way of thinking works by direct calculation for the sphere, because the number of conformal killing vectors is 3 and the number of moduli is 0. Okay, this also works in the torus. We'll examine the torus in great detail very soon, but on the torus we will find that the number of conformal killing vectors is 1. Just translations. Yeah. Translations in the Z direction, basically. Constant, yes. And the number of moduli is also 1. It's changing the tau parameter. Exactly, the complex ratio of the two signs of the torus. Okay, so the number of conformal killing vectors minus the number of moduli will also be equal to 0 as predicted. Now it is something that mathematicians have studied, and I'm just going to quote it to you, that for every higher genus there are no conformal killing vectors. Genus 2 and higher has no conformal killing vectors. No.
For torus, you can just identify two sides of a rectangle and you see that this is a torus.
Yes.
So you can see that other than constant, nothing is going to work.
Yes.
It has to be periodic with the period, and any other non-trivial constant will not satisfy.
Yes.
So this is only one. But other higher genus you have this kind of issue.
No, it's harder. Yeah, but it's going to be harder because you cannot just get away by identifying something flat without some curvature. Because we know that the integral of the curvature for any higher genus surface is non-zero. So you may hide that curvature in some identifications.
But if it is, my own thing is, it's not only identification, because if it is just identification, then constant will somehow survive it. You have to do something more, not just identification.
Yeah, right. Yeah. I don't even know. Yeah. We could probably try to think. Yeah, there should be, right? I don't know. I'm trying to understand why there are no conformal killing vectors on high.
Not just identification.
Yeah. I should know, right? I mean, what is the simplest way to describe, let's say, genus 2 surface? By hexagons, tell us about it, please.
Oh, you identify every other, so now there's a square, you have this side and this side, you identify 1 and 3, 2 and 4, and then you have to have a 2 and done, and you just identify the first one, and the third one, the second one, and the fourth one, and then you just...
You need more condition on just identification.
But it can't be the
Logically, this will give you the...
topologically, but it can't be the flat metric on this. Because were it to be the flat metric, the integral of R on this would be 0. But it's not 0, right? Right? So you need to know the complex structure for this, to do this, right? So it's something more complicated. I don't know. Yeah. Okay. But I'm just going to trust my friends from next across the corridor. Yeah. I'm just going to trust my friends from across the corridor who tell me that there are no conformal killing vectors on this, and they also know the number of moduli, and it agrees with 3 times g minus 1, but we proved it. Okay. If you believe that there are no conformal killing vectors, since we know the difference, we know that this is the number of moduli. So now we figured out, now we understand in more detail one aspect of this formula for string scattering amplitudes. Okay, I told you about if there were conformal killing vectors, if there were unfixed gauge and gauge diffeomorphism and Weyl transformations, then you would have to put some of these C insertions. And if there were these moduli, you have to do this. Now we know when this happens. Okay? So if you're doing a genus 2 calculation, you will have no fixed C vertex operators because there are no conformal. None of the vertex, all the vertex operators will be integrated over, and you will have to integrate over the 3 moduli in the problem. Okay? So yeah, it's a very concrete thing. Okay, any questions or comments about this before we proceed? Okay, there's one last thing I wanted to tell you about this BCCFT before we move on to the discussion of the BRST transformation properties of this theory. And that one last thing is also sort of interesting, and it's interesting because it illustrates the difference between this beautiful conformal normal ordering that we have been doing to define operators and something that you might more easily find yourself doing, namely oscillator normal ordering. An oscillator normal ordering. Okay, so let us remember what we had was we had an expansion of C. C was equal to some m is equal to minus infinity to infinity, Cm divided by z to the power m minus 1. We also had an expansion of B. B was equal to sum over n is equal to minus infinity to infinity, Bm over z to the power m plus 1. And you remember we had this BmCn is equal to, okay, let's do it this way. Minus n is equal to 1 and delta mn, so make it m. Everything else is 0. Okay, and for both positive and negative. This was just true. M positive and negative. Now we also know that positive m's lower energy, whereas negative m's raise energy. So something that in your first class in quantum field theory someone has told you at some point is that in free theories it's useful to normal order. That is, whenever you have an expression involving oscillators, you put all the annihilation operators to the right and the creation operators to the left. Okay? And this is useful because this operator will then annihilate the vacuum. Okay? So given an expression like C of z, B of z, this ghost number current operator, we defined it by this conformal normal, right? Which was, you separate them at points, you subtract away the 2-point function, and then you take the limit. Okay? But if we weren't so sophisticated, you might have defined it in another way, just by oscillator normal ordering. Okay? You might have defined it in another way just by oscillator normal ordering. And the rule might have been put every positive guy to the right and negative guy to the left. We need an additional rule for 0. What?
Some algebra, conformal algebra, how this current terms from the space.
Well, it's just a question of whether you want the plus vacuum to be annihilated It's a question of whether you want this guy to be annihilated by or the other guy. So there's some choice. Okay? Let us arbitrarily make a choice, and then we can switch it around.
In both cases, we get all other algebra satisfied.
Yeah. Everything is correct. The algebra is all right.
Algebra does not.
It's just a question of which state you want to be annihilated by your normal ordered operator. Plus or minus. I think we had defined that B0 on down was 0, right? So let us choose the down vacuum. Okay? So when we have a B and a C, a B0 and a C0, we'll always put the B0 to front.
So why is it so objective that this choice will not change in the algebra?
What algebra?
You define your normal order in conformal and Weyl.
Yes.
That gives you all this algebra. Now instead of doing all this, you define the left, put the positives on the right, and for the zero position, you put some thing like that zero position.
Yeah. So what it will do is to shift any bilinear by a constant. The constant would be 30. It won't affect any algebra. I mean, it might affect, it'll affect, see, what it might do is change what you mean by the Fourier modes. It won't affect any OP of the currents, any singular part in the OP of the currents. See, what it will do is this, that if you take your current and Fourier transform it to get the zero part, okay, that will shift by a constant compared to me. But that's the only change. And that constant shift will depend on how precisely you define your normal order.
All I'm saying is that you have a C0 D0.
Yes.
In front of that, you can put a plus or a minus or something like that, right? Ordering, you don't know what order to put.
No, if we change ordering, we'll also switch signs.
Yes. So you will put some number times C0 D0.
What do you mean put some number? Suppose I had in this expression here a C0 B0. Okay? It will be, your normal order will be interpreted as this number on the right. Another guy, you might instead have interpreted as C0 B0 with a minus on the left.
But you could have written B0 C0 also or not?
No. We're going to choose the sign to be whatever it is. It's just whether to be on the right or to the left. Yeah, so that would be a serious thing. To change the sign would be a serious change in the current. This is just this is just changing it by a constant. Okay. Okay, great. Not right. Yeah. No, we won't do anything. That would be an ugly thing to do. Yeah. Okay. So now let us do the following. What I want to do now is to find the connection between the operator defined by this conformal normal order and the operator defined by oscillator normal order. Okay? So let's do that. Just some very simple exercise. Okay. So let me see. So what was my conformally normal ordered operator? My conformally normal ordered operator was C of Z, let's say C of Z1, B of Z2, minus 1 by Z12, limit Z1 goes to Z2. Okay, that was the conformal normal order. Now let me get a similar expression for the operator normal order operator. So similarly, what I'll do is take C of Z1, B of Z2, and then I have to subtract out the part that makes this normal order. So let me explain what I mean. Let's take this and just write it out. Okay, so this is sum over m Cm by Z1 to the power m minus 1. This is sum over n Bn by Z2 to the power n plus 2. All good? Okay, so that's what the object here was. But now what we're going to do is to replace this by the operator normal ordered guy. What it means is that whenever this m is greater than so the normal ordering only there's only a difference when these two are equal, because otherwise they anti-commute with each other. So which order you put it in with the sign makes no difference. Okay, so what we're going to do, the thing that we do, which is the normal ordering, by putting all the C's, all the minuses to the right, no, all the pluses to the right of the minuses, only makes a difference when these m's and n's are equal. Also, it only makes a difference when this guy was positive and this guy was negative. Okay, so it's this term, namely sum over m, Cm, m is equal to 0 to infinity. In fact, m is equal to 1 to infinity, because we have agreed to put b0 to the right. Okay, so m is equal to 1 to infinity.
So what's the normal ordering convention, that b0 is to the right of c0,
and otherwise every positive guy is to the right of every positive guy is to the right of every negative guy. Okay, so
what if both are positive?
both are positive makes no difference, because only when they anti-commute that there is an issue.
Right.
When the anti-commutator is non-zero.
Right. Okay.
Okay. So when you see, it's only when the anti-commutator is non-zero that there is any issue.
Yeah.
So that's when m is equal to minus n. Now when m is equal to minus n and m is negative, then this is correctly operator normal order. We don't have to do anything. But it's this term here, which in the actual operator is this b minus m and z2 1 by z2 to the power minus m plus 2. This term is replaced by, this term goes to, almost, but these shifts make it not quite. And that will make a difference. Okay? This term is replaced by b minus m cm by the same stuff. Okay? So what's the difference between the actual and the normal order? It's this. So and this will replace by this with a minus sign, as in the reply to Indrani. So the difference between these two is this guy with a 1. Okay? And so we conclude that C of Z1, B of Z2 is equal to, Pulchinski has some symbol, some strange symbol. C of Z1 for operator normal order, B of Z2, this is operator normal order, plus this stuff 1 by m is equal to 1 to infinity 1 by z1 to the power m minus 1, z2 to the power minus m plus 2. Yes, we will. But first let's work it out, and then we'll take that limit. Okay? So, now we just have to work this object out, so that's very easy. Because we get z2 by z1 to the power m and then we have z1 by z2 square. Okay, and this thing is summed m is equal to 1 to infinity. So that's z1 by z2 to the power 2 into 1 minus 1 over is z2 by z1 over 1 minus z2 by z1. Okay, so that is what that is z1 z2 okay, z1 by z2 over 1 by z12. Do you agree? Okay, now in the limit z1 goes to z2, naively it goes to the same thing that you subtract out here. Right? So, naively it goes to the same thing that you subtract out here, but remember that the thing you're subtracting out is singular in the limit z1 goes to z2. So the difference between the two could tend to something finite. Okay, let's check it out. So what we have here is conformal normal order minus star normal order. Okay, so conformal normal order minus star normal order is this minus is equal to 1 by z12 into z1 by z2 minus 1. Okay, which is equal to 1 by z2. Okay, 1 by z2 excellent. I flip the sign. Let's see. The conformal normal order is defined as this minus this. Okay, and operator normal order is this. Yeah, operator normal order is this minus that. So, I tried to get the sign right. I messed up. Okay. Okay. Now, what does this 1 by z2 mean? 1 by z2. Remember in the current. So what we've got is that J host conformal normal order minus J host op normal order is equal to 1 by z. Now we take the limit z1 goes to z, both are z. But remember how we expanded out J host. Jg was equal to but z12 cancels z. Okay? So J host was equal to Jm by z to the power m plus 1. So if you've got a shift in 1 by z, you've got a shift in J0. Okay? So what we've concluded is that J0 conf is equal to J0 operator normal order plus 1. So if you take the operator normal order guy and you expand it the way we like to expand, or you take the conformal normal order guy and you expand it the way we like to expand, the two will differ by 1. Good? Okay. And by other symmetry.
It is already determined.
Yes.
And this one is going to be related with the anomaly current element. It will change that anomaly factor.
It's just going to tell us what the host number of the vacuum is.
But with this new current, if you just do your calculation for the JJ commutator.
With the new current, if you do your calculation for the JJ commutator, yeah, it will make no difference because it's just shifting the whole. Yeah, it's no right, but it's something that's proportional to identity.
Is it going to change the anomaly here or not?
No, it will change nothing. It's just different ways of regulating the same thing. Wait, let me get your.
That should be consistent because if it changes, then I will be asking you a question.
No, it still change nothing. This is just some, regulation of the. It's just adding a bit of identity with 1 by z to this current. But let me think about your question just one. What you are saying, actually, the thing that is causing the confusion is this. The thing about this operator normal ordering that is funny is that it is not translational. Okay? This was this, that it did not depend just on Z12. Okay? Because by defining operators, we chose a point. We chose to do we chose the origin as the place to do radial quantization around. And operators are defined with respect to this origin. Okay? And then by doing this subtraction, we're getting something which subtracts out 1 by z, which is something completely impossible if you're working in a translational invariant. But what we're doing here is breaking the translational invariance. Okay? This is why it would be such a stupid thing to do if you actually wanted to work with this theory. Okay? But it's good for just one thing. So we would never do this. This would not be a, we would only be defining these currents in this. We would be violating translational invariance in this definition.
Yeah,
okay, so it's a very silly thing to do for most purposes. It's good for exactly one thing. Okay? It's good to figure out what the charge of the vacuum is. Because we know by definition that J0 operator normal ordered, that the charge, operator normal ordered charge of the vacuum is 0. Because the operator normal ordered charge is the integral of J0, but operator normal order, and the operator normal ordering is done in such a way that it annihilates the down vacuum. Okay? So this is the only good reason to do this exercise. Anything else, to work on this, it's a very stupid way of functioning. Okay? But for this reason, it's quite good. So what have we concluded? We've concluded that the conformal normal ordered charge of the down vacuum is 1. Now, if you don't like all this operator normal ordering and so on, you could have concluded the same thing much more easily using Indranil's prescription from the last class. Indranil's prescription was, if you're getting things right, then the state corresponding identity better have charge 0, and therefore the state corresponding to the vacuum has an additional charge of 1 because the vacuum was C. Was the operator C. Operator C has ghost number 1 larger than the ghost number of the vacuum. State corresponding to vacuum better have charge 0. So the identity state, the vacuum state, the ground state, this down state, okay? This state has ghost number 1. We've just derived that much more painstakingly through this way of thinking. I could have given you the answer very fast using our reasoning, but I wanted you to see this business just so that you understand that the conformal normal ordering we're doing is closely related to, but is not exactly equal to, the operator normal ordering that you would, if you were a naive, you would just done a first course in quantum field theory and you're working on the cylinder. This is presumably what you would have done. You just normal order the operators. That's not exactly equal to this conformal ordering, but it's useful for some purposes. And in particular, you can use it to figure out the charge of the vacuum. Okay. By the way, what is the charge of up? No, B acting on C0. B0 kills it.
C0.
Well, C0 acting on down makes up. This is killed. B0 on down is equal to 0. Right? That's why we put B0 to the right.
Okay.
We calculated the charge of the thing such that was annihilated by B0. Okay? And so this guy is going with the fact that if you guys have done the exercise from last class, that del Cc was the operator that creates that state. Okay? And did anyone work out the state corresponding to the operator B? Okay, please work it out and check from every point of view that state has the right ghost number. From the operator point of view, it's very clear. It should have ghost number -1 because it's -1 relative to the state corresponding to identity. Okay? But now what's going on here? You're starting with a vacuum which has -1. What are you doing? So just check, work it out and check.
C0 acting on up is 0 or not?
What? C0 acting on up is 0, yes.
C0 has ghost number what? 1.
Every mode in C has ghost number 1, yes.
1. Is this equation, if up is ghost number 2,
Yes?
then what is the whole ghost number of the left hand side right? The right hand side is 0.
Sorry, what equation are you looking at?
C0
C0
acting on
up is equal to 0. Yes? So there's a ghost number 3 state which is 0. So that state doesn't exist. There's no problem.
Would have been a problem if it as you were.
Had it been another state whose ghost number you knew was not 3, then it would have been a problem.
The ghost number anything can be is related to 0.
Sure. I mean, it's just in the Hilbert, part of the Hilbert space that has some ghost number. You write down a state, but it happens to be 0. Yeah. Okay. Equating to 0 is not an issue. Equating to yeah. You see, because what is the reason that you can't equate things? You do the transformation. If two things transform with different phases, then you're in trouble. But yeah, all phases leave it invariant. Okay. Yeah. No. Okay. So this is all I wanted to say about ghost number, BC system. We want to remember, of course, that the ghost number of the vacuum, of this down vacuum, is 1. One way of remembering it is that it's dual to the state C, which has ghost number 1. Okay. This you probably will never use. I just wanted to show you, that what this conformal normal ordering is in terms of something more familiar. Okay.
So in this theory, if you say that what is this amplitude between mach 1 to mach 1, usually that becomes e to the power action and path integration.
Yes.
The action that we have, what is that?
Okay. Now you're asking, if I compute e to the power minus s, what is this interpretation in Hamiltonian language? We will go through this. You see, clearly it has to have 3 insertions of c if we're doing it on the sphere. Okay. So we'll have to work this out. This is the Zama logic of business. We'll have to work this out. Let me postpone that. Okay.
What is this geometrical diffusion or something? What?
It's to give a clean Hamiltonian slicing of this action. It involves a careful treatment of the zero. A careful definition of the inner product and so on. We will go through that when we come to the operator way of making it. Okay. And the zero modes, of course, complicate matters. Otherwise, it's all simple. We'll get to that at some point. Okay. That was your question? Yeah. We'll get to it. Okay. Fine. So now, that's all I wanted to say about the BCCFT by itself. Okay. Now for the rest of this lecture, we won't go on too long, and I'm sorry I keep you guys so late. For the rest of this lecture, we will just start addressing. Okay. We will just start addressing. You can call me Shiraz. Yeah.
Before we move on from the next, before we move on from the BC system, at no point do we figure out that like those don't actually show up.
Show up in the amplitudes?
Right, that was like just using paper.
Yes,
As
yes.
you introduce them, you just make.
You don't want them. Yes.
Right.
That's what we're going to go on to now.
Oh, okay.
Yes. Okay. The way you do it in a clean treatment in quantum field theory is by using BRST symmetry.
Yeah.
Okay. And that's what we're going to do now. Okay. So now we've got, so let's start motivating this thing. Let's rewrite now that we understand things even better than we did before, let's rewrite our scattering amplitude formula. Our formula for scattering amplitudes was integral over moduli, dTm, then a factor of b del g by del t for each modulus. Then for every conformal killing vector, there was a c times v of sigma. Then there was a factor of integrated square root g. Okay, there was a factor of integrated square root g t2z v's for the remaining guys, and then of course we had dx and dc db exponential of minus matter action minus ghost action. Okay. So this formula, we're beginning to understand more and more things about it. By now we understand the conformal field theory governed by the matter rather well. We understand the conformal field theory governed by the ghosts rather well. We spent the last 2 or 3 lectures working on all kinds of aspects of it. Okay? We understand the number of these moduli and the number of these CKVs rather well. The things are getting more concrete. What we have not been careful to try to understand is what are these V's that we should put into this formula. Okay? In some class I gave you a very rough answer to this question. I told you that these V's had better be dimension 1, 1 primaries in order that the insertions preserve Weyl invariance. Right? We were very careful that to ensure that the path integral with this measure was Weyl invariant. Weyl invariance in this gauge fixed form is simply a question of whether the answer depends on the particular metric you have chosen, the Weyl factor of the gauge fixing metric you have chosen. Okay? Now, every time we have a V, we have a square root G. Square root g is transformed with while weight 1. So the v's had better remove that transformation. And it will do that provided that these vertex operators are scalars, so they don't transform under diffeomorphism. That of course, because there has to be diffeomorphism invariant. But with conformal dimensions 1, 1. Then if they're scalars, all of their conformal dimension comes from how they transform under Weyl transformations. And 1, 1 is exactly what will cancel the transformation of square root g. This we've already seen. So this formula had better, we know, v is equal to 1, 1, some 1, 1 primary operator. Okay, this we know. If it's anything other than primary, it will pick up, under Weyl transformations, pick up derivatives of the Weyl factor. So it has to be primary because it has to be homogeneous, 1, 1 because it has to be that weight. That's great. This we know. Okay, but now you might be a bit worried because 1, 1 primary operator of what theory? The matter, the ghost, some combination. Just from the point of view of conformal invariance, it looks like anything goes. Now we are in the danger of doing something very wrong from two different points of view. Firstly, if we look at 1, 1 primaries from the ghost sector, it's sort of intuitively clear that there was no corresponding object of that sort in the Nambu-Goto theory. The ghost was just something to get the measures right. We start scattering states associated with the ghosts. Looks pretty bad, right? Okay, at the intuitive level, that's clear. But suppose somebody takes the point of view that okay, maybe Nambu-Goto was just a starting point for this whole thing, and as long as what I get is consistent, I'm okay. You could ask just from the internal consistency point of view, what would go wrong? What are the issues with this ghost? And we're going to see this in great detail as we go on with our course. But I'm going to give you a preview. And the preview is this, that
BRST charge will not be conformal if you put random ghost in
the BRST charge.
You want, once you construct BRST charge, you want this whole thing to be invariant.
Well, the physical problem that will go wrong, perhaps related to what you're saying, the physical thing that will go wrong is that you see, there is a built-in tension in what we're doing. Exactly like in quantum field theory when you introduce ghosts. And the built-in tension is that we've introduced we've got a non-unitary pair. Okay? Now, it may not be totally clear that non-unitarity on the world sheet will translate to non-unitarity in space-time, but it will. Okay? So, if we allow for, remember every time we have a vertex operator there is a corresponding state from the state operator correspondence. If we allow for states with negative norms to be scattered, okay? If we allow for states with negative norms to be scattered, we will end up producing a non-unitary theory of space-time. We will see this in great detail as well. Moreover, you may take the point of view, and this is what's really dangerous. You may take the point of view that, okay, I will only stick to some good states with positive norms, to be scattered. Spin statistics. The spin statistic, in space-time at this point we've only got bosons. So space-time spin statistics will not be an issue. But hang on, I see where you're going and we'll address some of these issues. However, you see when we compute, let's say a 4-point function, let's say four particle scattering. We've got some 4 operators inserted on the world sheet. Okay? You know the 4-point functions in any conformal field theory, in particular conformal field theories in this 2-dimensional space, can be expanded in operator product expansion. Seems intuitively clear that this operator product expansion in space-time will turn into this tree diagram for the S matrix. Okay? If we do this on the sphere. And this will turn out to be correct. So even if we scatter good states, if there is a non-zero contribution to the OP for these good states producing bad states, then that will also violate space-time unitarity, because you will have hosts propagating in intermediate channels, even though you've declared that they don't occur in your theory. Everything I'm saying is exactly the same issues that arise in quantum field theories when you introduce ghosts during gauge fixing. Okay? So the lesson is the following. The lesson is that what we want to do is to make sure, A, that we only propagate good states, whatever that means, good vertex operators on the outset. B, we want to make sure that when we do that, only the good states continue to propagate in the middle. And the way to ensure such a thing is by using some sort of symmetry. Now, since we all have so much experience with BRST symmetry, we know that's what we want to do. So what we are going to do is to demonstrate here that this action has a BRST symmetry in it. We will compute the BRST charge. Because it's such a nice and beautiful conformal field theory, this BRST charge will be the integral of a current, BRST current. Okay? So it will be more useful, as always, that, to deal with the BRST current rather than the BRST charge. Okay? And the operators that we will allow to scatter are the operators that are annihilated by the BRST charge. In terms of current, it will be the statement that J BRST times V 0 by V by Z. Because the commutator, the thing is the coefficient of the 1 by Z part of the OP. So we are going to construct this BRST current.
This is the statement that this G has been Q.
Has to be Q closed. This is the same as the statement that Q BRST commutator V, yeah, in this case, since they'll all be bosonic, commutator is equal to 0. Oh, you know, if you build something that's anti-commutator, let's say with 1C, commutator, anti-commutator appropriately, because this will be fermionic.
And then can you add anything that is not Q exact to this V?
Exactly. Exactly. Then the next thing we will show, just this is the standard usual BRST story. Okay? The next thing we will show is that if V differs by V goes to V plus Q times U, the string scattering amplitude is unchanged.
That is what we will show.
We will show. And therefore, physical states, and we will then identify physical states with BRST cohomology. That is, states annihilated by Q, modulo states that are Q exact.
What you were saying, you're putting some ghost insertions in V.
Hmm?
If you allow for that,
Mhm.
which I allow for that,
Mhm.
then can you write some non-trivial function on ghost insertions till this Q BRST annihilate the whole action?
Sure, you can. In particular, it's a
They are not going to be exact. Exacts are not used, forgetting them.
forgetting things that are exact. Yeah, you see, but it's a bit hard to make your question precise because states are associated with equivalence classes.
Yes.
So perhaps your question is, in every equivalence class, is there a representative with no hosts? That's maybe a precise version of your question.
You will go to, you will start talking about BRST. BRST is symmetry of your action.
Yes.
First you have to show that your action that you have written down.
Yes.
That is invalid.
Yeah, we'll show that. Yes.
Now, you are saying that why in V just allow matter and that's all. Put some ghost stuff if you want.
Put whatever you want. You see, we're going to make a rule. The rule is going to be that for every allowed state, every physical state, corresponds to a BRST. I mean, allowed states correspond to BRST cohomology. So allowed scattering states are not states in the field theory. They're equivalence classes.
Yes.
Okay?
Yes.
So now your question is, do all allowed states, I mean, are there allowed states with ghosts? Okay, it's not very precise because allowed physical states are equivalence classes in this two-dimensional conformal field theory.
If you have any one way of cutting so that in that way you have no ghost, then you are good.
Then you're good, exactly. So that's your question. Is there a representative in every equivalence class with no ghosts? And we will show that that's true. Okay? Moreover, we will also show that the inner product on the space of BRST equivalence classes is positive definite. And we will also show that the space of BRST equivalence classes, the space taste of physical states, the BRST closed modulo BRST exact, gives you precisely one-to-one correspondence with the spectrum we found in light content. Okay? Once we have understood all of these things, then we really understand this formula. Because then we know what these V's are. V's are any representatives of BRST cohomology, and these V's are in one-to-one correspondence with the physical spectrum of the theory that we derived so long ago, right at the beginning of the class. And that's very satisfying because that tells you that what you're really doing now is doing what you would have done had you been doing Nambu-Goto. Okay? All this we will turn to in our next class. No, not today. Questions, comments, or questions?
Anomaly aside, is there any reason why I couldn't see if there's any reason why I couldn't gauge that you want to see that we have in the PCF?
Okay.
Usually gauging a symmetry is not something that you want to do. So you have to do it. It's not really, it's usually not.
Well,
Right, you can't do global set.
can't take global sets. Let's see. Let's see. You know, take Wilson-Fisher theory with a complex field. It has a global U unsymmetry. That's fine. You see, the gauging that we do is only the gauging that is forced to us by logic. Why did we gauge diffeomorphism on the world sheet? We gauged it because our original Nambu-Goto action, you know, two configurations that differed by diffeomorphism were the same configuration in space-time. What we wanted to do was to sum over all maps, all surfaces in space-time. The coordinates made no difference. That's why we gauged the diffeomorphism. Why did we gauge Weyl transformation? We did it because in the transition between Nambu-Goto and Polyakov, it was a transition between equivalence classes. One solution of Nambu-Goto went to a Weyl equivalence class of Polyakov. That's why we gauge. Now, gauging is a serious thing. Gauging is a serious thing because it tells you that two states that differ by gauge transformation are not physically distinct. Okay? Unless we have a physical reason to do that, we don't do it. You know, we had a well-posed problem, we're trying to address that problem.
I'm just saying from the perspective of somebody hands me a Lagrange theorem, right? And says what are the symmetries of this? When someone hands me an action, says what are the symmetries of this? If you see a symmetry that's you can write down globally, usually the next step is write it down locally, right?
I mean, for some purposes.
Right, because in sort of the cases of the Nambu-Goto action, you had a mental picture of what you were looking for. So you weren't really starting from the Lagrange. You were starting from an idea of like, oh, it's a length minimizing on a string to sort of go to area minimizing or volume minimizing. But suppose I didn't know the physical implementation of the system. Somebody just handed me this wrote this down and said, okay, what are the symmetries here? Right? So I'm just saying, somebody hands me this Lagrange, somebody hands me that Lagrange, and there's no obvious reason for me to go, well, in this case I'm going to gauge it, in this case I'm not.
Well, I just want to say again, there are many physical quantum field theories that have global symmetries. Take QCD with NF flavors, this is SUNF times U1.
Yeah. But there is a goal, but there's also like the whole game of Young-Mills theories, because
No, I mean, I agree. Sometimes it's useful to gauge things, but sometimes you don't.
I mean, the real reason why you gauge Young-Mills theories is not for this measure, for what you want to, because in some sense they're taking sections of some very complicated problems and not, they're not defined on the data.
Well, there are theories with non-abelian U1 global symmetries. So there's no reason you have to, if you see a non-abelian, sorry, UN symmetry, there's no reason that you have to gauge it. It's a choice. I mean, consistency doesn't force you to do it. You either do it or you don't. You get very different theories, right?
Yeah.
So
So what is it, for example, let's say that in electromagnetism forces you to gauge the theory, but
You wanted to-
looking at these are both U1, these are both theories with U1 symmetry.
you wanted to build a theory with a spin 1 massless degree of freedom. Gauging allows you to do that. But there's no logical reason. You take a theory with a U1 global symmetry. Nothing wrong with that. Wilson-Fisher theory with complex scalar is such a theory. It's won a Nobel Prize. Yes. Yes.
Why don't you first see some great trouble?
In
Scattering matrix will not have both superposition. Why don't you first see the trouble?
okay. Now you know if you, so you don't gauge Y. That's what you're saying.
Not gauge well, but keep it have some C factor. So it's not right kind of gauging.
So for instance, you're going to get your answer will depend on exactly what base metric you choose. G0. But apart from that, we will see it in the BRST symmetry. We will see that the BRST
Yield potential something.
exactly.
We're only dealing with the BRST because we're dealing with the BC system because we have the gauge in the first place, right?
Yeah.
So it sort of works the other
So-
way.
so
If I don't gauge that, I never deal with this.
I agree. So you could ask different questions. I think Indranil's question was, suppose I just choose some G0.
Yeah.
I look at the scattering formula. I forget. Okay, yeah, if I choose a different G0, I choose a different G0, I get something different. Doesn't matter. Maybe I've got a 1 parameter set, a G0 parameter set of theories. Okay, but okay, yeah, I've got some scattering matrix. What at the level of just somebody gives you this formula and declares this is the scattering matrix in space-time. How will you see that it can't be? That doesn't define a well-defined space-time. And you will see it in this way. Okay. When you compute J BRST of Z with J BRST at 0, you will find C matter minus 26 over Z in this formula.
This BRST is for gauging the both.
This BRST is the thing that will allow you to make a sensible cut down on your set of V's. So you lose unitarity in space-time. Okay, this thing turns into the formula J BRST square is equal to this quantity. Now it's this quantity, and it's only 0 in C equals 26. Okay, so the whole BRST procedure of taking it makes no sense. The whole thing about taking these equivalence classes makes no sense. You will find no way, you will be forced to deal with every 1-1 primary in the theory. You will be forced to deal with negative norms and unitarity in space-time. Okay, so that's actually a good question. It's true that from every point of view, at any point, if you say, okay, I don't care what came before, but let me just go with this, you'll see trouble at that stage. It's a very tight structure. Now, there's another question that came up that maybe you're asking, which is a good question, which is, suppose I take this formula and let C not be equal to 26. Now I do my path integral, including the path integral over the y factor of the matrix, and I don't gauge it. I can't gauge it because things depend on it. I just don't gauge it. I increase the number of directions that I do my path integral. path integrals over my matter fields, plus the Weyl factor. Could that possibly give us something sensible? This turns out to give something called non-critical string theory. Okay? This Weyl factor can be thought of, roughly speaking, as another direction. Apart from your, let's say you started with, instead of 26, you started with 4 matter fields. So 4 Lorentz invariant directions of space-time is another direction of space-time, but one in which has no symmetry of rotation of this direction into the other form. Okay? And this, people have tried to interpret this as a particular warped compactification of string theory. In fact, Spenta has worked at this. Spenta and Gautam and so on had many papers. I'm not exactly sure what the status of that is, but it's an interesting question and not obviously meaningless. Okay? That is a thing one could try to do. There are what? Don't gauge at all. Yeah. Then you're not getting a string propagating in the directions you want it to. Say you start.
That seems to be right, because if I gauge and I have an anomaly, this seems like I'm doing fundamentally right.
Yeah, exactly. Yeah, you don't do that. Now, it's not clear that it will work out okay, but it might. It has a better chance. Yeah, and there was a long discussion in the 90s which the TIFR group played a very active role in, but somehow I find it very confusing what the outcome of that was. So it's a bit hard to summarize, but at least in some situations it works out okay. I'll refer you to Gautam about this. Okay. Any other quick questions, comments? Okay. Now I'll just give you where we are in this. In 2 or 3 lectures, we will have completed the first 5 chapters of this book, and then we will move on to the superstring. You see, because this was so light, so technically light, it's whetted our appetite for technicalities. Okay. Oh, I'll take your advice. One possibility is then at that point we have a fork. The fork that Polchinski takes is do physics with the bosonic string. Yeah, that's satisfying because you're doing physics, but it's unsatisfying because you're doing physics in a theory you know to be meaningless. Okay. You can do physics with limited technicalities. The other branch of the fork is to complete the technicalities and then do the real stuff. I'll take your guys' advice. Depending on what your level of exhaustion with technicality is, we can take that call. Okay. But we'll have another maybe 3 or maybe 4 lectures for this stuff.